Hello, I'm David Patterson. I'm a retired research scientist from CSIRO in Australia. I have a degree in applied mathematics, in engineering, and I have a PhD in engineering. I'm going to talk to you today about infinity. This is a huge topic, not so much because infinity is large, but because people have invented so many different systems of infinite numbers. Some of these systems have infinitesimals and some don't. Some of these systems have infinity equals infinity plus 1, and some have infinity is not equal to infinity plus 1. The infinity that you're taught in school is not intuitive or useful in applied mathematics. The infinity that I'm going to introduce to you is both intuitive and useful. It's called ordinal infinity, and it's been around for a lot longer than the infinity that you were taught in school. When I've completed this series of talks, there are going to be 8 parts, I hope. Parts 4, 5 and 6 are applications in fields other than pure mathematics. So part 4 is applications of ordinal infinity in quantum mechanics. Now this is part 5, applications of ordinal infinity in computer programming, which should be a lot easier to understand than quantum mechanics. If you've ever heard of NP complete or NP hard, then you'll find some useful information in this talk. However, if you do any computer programming that requires calculating how long the computer program is going to run, then it'll be useful. I have to admit up front that I've learnt more about ordinal infinity from computer programming than I have learnt about computer programming from ordinal infinity. This slide is a quick review of parts 1, 2, 3 and 4. Ordinal infinity is written using the lowercase Greek omega. In talks part 1 and 2, I gave 4 ways to generate the field of ordinal infinite numbers. In part 3, I introduced a new limit that is a non-shift invariant fluctuation removing limit. What that means is that if you split a function into a mean part plus a pure fluctuation, then we define the limit as the value of the mean part at infinity. Part 4 talk was applications in quantum mechanics, in interpretation of quantum numbers, and how infinity helps with renormalisation. Computer programmers want to know how long their programs are going to run for. And for programs that are not in themselves infinite loop, the answer to that is given by computational complexity theory. Some problems are inherently difficult. A famous one is the travelling salesman problem. In other cases, it requires considerable effort to construct an algorithm that runs quickly. An efficient algorithm that sorts data is often quoted as an example. A simple-minded approach to sorting requires of order n squared operations. The advanced heap sort computer algorithm requires order of n log n operations. The difference in runtime is enormous. A heap sort algorithm can run up to 70,000 times as quickly as a simple sort. Algorithm speed ratios like that matter. Going back in time, the year is 1870. The man is Paul du Bois-Reymond. This is the time he publishes in French on the relative grandeur of infinite functions. In 1877, he enlarges that as on the paradoxes of infinity calculus. For English speakers, I thoroughly recommend an excellent exposition that was written by the mathematician Hardy in 1910. You may know Hardy as the mathematician who worked with Ramanujan. He wrote, "Orders of infinity, the infinita calcul of Paul du Bois-Reymond." The order of magnitude symbol itself, big O notation, dates from the year 1894, where it first appears in a physics textbook. In introducing this, I can't do better than to quote directly from Hardy's book. The notions of order of greatness or order of smallness of a function f of n, of a positive number n when n is large, or of a function f of x of a continuous variable x when x is large, are of the greatest importance even in the most elementary stages of mathematical analysis. The student soon learns that as x tends to infinity, then also x squared tends to infinity. And moreover, that x squared tends to infinity more rapidly than x, i.e. that the ratio x squared over x tends to infinity as well. And that x cubed tends to infinity more rapidly than x squared, and so on indefinitely. And it is not long before he begins to appreciate the idea of a scale of infinity, x to the power n, formed by the functions x, x squared, x cubed, etc. This scale may supplement and to some extent complete. This scale he may supplement and to some extent complete by the interpolation of fractional powers of x. And when he is familiar with the elements of the theory of the logarithmic and exponential functions, he will realize that the exponential function increases more rapidly than any power of x, and that log of x tends to infinity more slowly than any power of x. As we proceed further in analysis and come into contact with its most modern developments, such as the theory of Fourier series, the importance of these ideas becomes greater and greater. Given two functions f and phi, if f on phi tends to 0, then we write f is less than phi. This funny curly less than symbol is the notation used back in the year 1870. Modern computers, programmers, and physicists would write this as order of f is less than order of phi. From du Bois-Reymond, we get the idea of pan-tachy. Tachy as in tachometer, speed. The set of all speeds, i.e. all possible orders of infinity. Still, no one has a way of constructing a complete set of orders of magnitude of ordinal infinite numbers. Computer scientists have come closest. The following table comes from a computer scientist, and I have to apologize here up front because I don't remember the name of the person who created this table. The table gives a collection in order of orders of infinity. Here poly means arbitrary polynomial of, epsilon is an arbitrarily small number. The function such that function of n equals 2 to the power n is similar to the half-exponential function that I'll discuss 2 slides from here. The third last function symbolises tetration. Here we go. So the sequence here is 2, then 2 to the power 2, which is 4, then 2 to the power 2 to the power 2, which is 2 to the 4, which is 16, then 2 to the power 16, which is large, I think it's 64,000, and then the next one is 2 to the power 64,000. So that gets rather large rather quickly. A here, A of n, is the Ackermann function, and the last one, which is partly obscured, is BB of n, which is the inverse function up here, which is called busy beaver. Look those up if you don't know in Wikipedia, or if you don't know, you can look it up in Wolfram Alpha. For comparison purposes, all the main types of infinite number are written infinity in the table below. That is, using the lemniscate symbol. Types of infinity are written in order from coarser to finer resolution. In naive infinity, there's only one infinity, and 2 to the power infinity is just the same as infinity. For Cantor's cardinal infinity, we jump from one level of infinity to the next using exponentiation, but not if you multiply by infinity. Order of magnitude accepts that multiplication by infinity increases the level of infinity, but not multiplication by a constant. For instance, order of magnitude of n squared is greater than order of magnitude of 2n, but order of magnitude 2n is the same as order of magnitude n. Standard part plays a large role in Abraham Robinson's proof that what is true for real numbers is also true for infinite numbers. The standard part is a rejection of components that are minuscule compared to the largest component, and it's written standard part, ST, open brackets, close brackets. So the standard part of 2 omega plus 1, of 2 infinity plus 1, equals 2 omega, whereas the order of magnitude of 2 omega plus 1 is equal to omega. So that's the difference. The standard part of omega plus 1 equals omega. For computer programmers, the level that matters most to them is the standard part, because an algorithm with a larger standard part will take longer to compute. Logarithmic exponential numbers. Of the 45 orders of magnitude listed in the table 2 slides ago, 37 are logarithmic exponential numbers, and the remaining 8 are not. These are numbers derived from the functions function of x equals x, function of x equals exponential x equals e to the power x, together with a finite number of operations of plus, minus, times, divide, taking to a power, and taking the inverse function. We can't allow an infinite number of such operations, or we end up with cos of x, which fluctuates at infinity. So we're only allowing a finite number of operations. The logarithmic exponential numbers also go by the name Hardy field and transseries. There are subtle differences between these, but They're not important for this particular presentation. Almost every time you write a computer program, that is not an infinite loop, I mean, the running time will be given by an order of magnitude that is a logarithmic exponential number. These all have nice properties, like the absence of fluctuations at infinity. In addition to the logarithmic exponential functions, there are also a few special functions. 8 of the orders of magnitude on table 3 slides ago are special functions. Although these are easy to define on the integers, there is still some debate over whether there exist unique extensions to the real numbers. I claim that extensions to the real numbers exist and are unique with the property that they are very smooth in the sense that the differential exists and is monotonic defined as always increasing, always decreasing, or constant for all n. The special functions from 3 slides ago include the busy beaver function, which increases very rapidly, the Ackermann function, which also increases very rapidly, tetration, superlogarithm, and half-exponential functions. The superlogarithm is already designed to be very smooth and exist on all real numbers. Tetration is the inverse function of the superlogarithm, so is likewise well behaved on all the real numbers. Now I'm going to introduce the half-exponential function. This is the function f such that f of x equals e to the power x equals exponential x. The very smooth result, well, there are functions that satisfy this that are not smooth, but I believe that the smooth result is unique. This smooth result can be calculated from the Taylor series for e to the x. 1 plus x squared on 2 plus x cubed on 6 plus x to the 4th on 24 plus x to the 5th on 120 plus x to the 6th on 720, etc. The Taylor series for the half-exponential function f to order x to the power n is found by the simultaneous solution of n equations into n unknowns. Where there are multiple solutions, choose the one where all coefficients are real and positive. To n equals 3, the Taylor series for f is f equals this. First term is just slightly less than a half. So if you think of that, a half doesn't matter. First term is just slightly less than a half. The half-exponential function is just the start. Half can be replaced by any real number a. Inverse functions and fractional calculus generate far more special functions. There is a slight possibility, and this may be completely wishful thinking on my part, that special functions like the half-exponential function can help for NP problems in computer programming. It's been said that easy problems can run in polynomial time. Hard problems require times that are exponential. The half-exponential function and a-exponential functions all give runtimes intermediate between polynomial and exponential. Take-home messages. The order of magnitude is a symbol that is derived from ordinal infinity. The It's a statement about infinity. It's a statement about what happens to real numbers and integers at very large real numbers and integers. Computer programmers have given us the most complete catalogue of orders of magnitude. The standard part gives a more accurate calculation of computer runtime than order of magnitude alone. So to remind you, the standard part of 2 omega, the standard part of 2 times infinity is 2 times infinity. But the order of magnitude of 2 times infinity is infinity. Trans-series are good, but are not complete even for practical computer programming problems. In addition to trans-series, there are also special functions that may be useful. That's the end of this talk. The next talk will be about the applications of ordinal infinity in solving divergent series.